Okay, so what we've got here, this little spinning thing, this is actually like a magnet that's balanced on a needle. Look, it gets attracted to one end of the magnet and repelled from the opposite end. So what we're going to do is use this spinning magnet to investigate a little bit what's the effect of an electric current on a magnetic field. And what we can see is that when we hold the wire there, do you see how it moved the compass? So that the compass is pointing, or the magnet on a point, it is a compass, and a compass is just like a magnet on a needle, is always pointing like at right angles to the wire. Like I can steer the compass by moving the wire, and in fact what's really interesting is that if we go underneath, it completely flips direction. And so that gives us the idea that when we have this electric current flowing through a wire, that the electric current comes out of the plus terminal and it goes around the wire and into the minus terminal. And so the way we can build an understanding of this is that the magnetic field goes around the wire, like it's making circles around the wire, kind of like the circles on like a darts board. And the way we can find the direction of those circles, because remember, magnetic field shows us which way we're pushing a north pole of a magnet, we can use what we call the right hand grip rule. So your thumb points along the wire in the same direction as what the current's going, and your fingers wrap around the wire in the same direction as the magnetic field does. So at the moment the magnetic field is going around the wire that way. And that this is really amazing. Like we can create a magnetic field, we can move magnets just by having electricity flying around and around in a wire. This is the start of how we're going to build things like electromagnets and motors and generators and all of those cool things that are like electricity and magnetism combined. The strength of the magnetic field gets weaker and weaker and weaker the further we move away from that. So when I hold it really close, I can have a pretty strong impact on the direction the compass is pointing. But if I move it a little bit away, it will just go back to where it was pointing naturally because of the Earth's magnetic field. Like it's pointing to north over that way, or over that way. Anyway, does that kind of make sense? So the strength of the magnetic field depends on how close the wire is to the thing that we're interested in, and it also depends on how big the current is. Like if we put a bigger current, we get more magnetic field, a smaller current, less magnetic field, and the direction of the magnetic field is the right hand grip rule. I'm just going to write down a few of those things. Cool. So first of all, thinking about the strength of the magnetic field, the letter we use for the strength of magnetic field is B. And we measure it in Tesla's, T. The I is the electric current, and amps, the D is the distance from the wire, and meters. And this K, it's just some number that makes it work. Which number? It's 2 times 10 to the power of negative 7. It's a really small number, but it's a number that makes the maths work. It's how we get electric current and distance to turn into magnetic field strength. And so here is our right hand drawn like that, and that helps us see that if we have an electric current flowing through a wire, the magnetic field, because of that, is going to make kind of circles around the wire. So you can see that they're going around and around and around the wire, kind of spreading out from it as though the wire is going through the centre of a dartboard, and the different circles on the dartboard are showing you the loops of the magnetic field. And you can see, you're meant to be able to see, that it's curving around It's going behind the wire at the back and in front, on the way down. So up on the back and down on the front.